Hello everyone. Uh, Greetings from my side. My name is Anirban Gupta. I have done my MSc and MPhil in physics, and I am doing my PhD in the field of architectural acoustics from the Savitribai Phule Pune University, Pune. I have completed my pre-viva and yet to appear for the final vivas. Well, about me, I'm a teacher with more than 1 decade of experience in the field of education. I have trained students from science and engineering background, both from UG level to the PG level. Apart from academics, I have done my IELTS and I'm also a certified coach from the Transformation Academy USA. I'm also a soft skill trainer and I have taken care of the soft skill training departments of my institute, and I take pleasure in nurturing the creative ability in students so as to make them able to present themselves in the society without any limitations, inhibitions, or uh, anxiety. Right. My core competencies, I would say, is I can present myself in a good way amongst the people in the society. I can I can develop a learning environment in my classes. I have a good lesson plan design ability, and I can use varied teaching techniques, right? Depending on what are the needs of the students of the class that I'm teaching in. I can identify the students' needs and be empathetic towards students, and I believe I have a good communication skills to deal with my students. Uh, Apart from that, what I have done throughout my career is that I have represented my institutes in Avishkar research competitions, which are organized by the University of Pune and the University of Mumbai both. I have won the Young Researcher Award in 2020 very recently. I received it from Institute of Scholars. Uh, I have uh, I have taken part in several competitions which are organized during the Hindi Pakhwada, that is the Hindi Divas, and I have represented my district in many of such events. I have done quite a few workshops, 10 to be very precise. I have done a number of certified programs, around 16 certified programs, which include certifications from NPTEL, certifications from Google, certifications from foreign languages like French. I have done a bit of German course, and I have done a soft skill training programs which are organized by the MHRDs, and I have done the soft skill and life coaching from Transformation Academy USA. The certificate programs I have done also includes certificate programs from several IITs and HBCAC and BARC as well. I'm a member of esteemed professional bodies like IOA, that is Institute of Acoustics UK, in which I am a student member since past 3 years. I am a member of International Association of Engineers, a life member of that. I am a life member of Institute of Scholars, and I am a yearly member of IAPT, that is Indian Association of Physics Teachers. Right. Apart from that, I have attended and presented papers in 14 conferences. I have 7 peer-reviewed journal publications, which includes journals from Scopus and which are listed, the journals which are listed in Scopus and UGC Care list. One national paper in National Journal, one paper in National Journal, and 4 conference proceedings. Right. I have also done faculty development programs around 17 in numbers in all these during all these years. Apart from academic field, I have also handled quite a few responsibilities, additional responsibilities in the institute that I have worked with. I'm a member of, I'm the coordinator of University Industry Interaction Cell, which is known as UIIC. I am training in charge, training coordinator of the placement and training department of my institute. I was the in charge of admissions committee of my institute, which is a big responsibility for any science institute, I believe. I have worked as the project guide for Avishkar inter-university project research project competitions. I I have also been invited as a resource person for a couple of workshops and programs that are held in various institutes in Maharashtra and Tamil Nadu. I have also worked in the affiliation committee. I was the coordinator of the NAC Criteria 3 team in my institute. Apart from that, I have also judged, invited as a judge on 3 occasions in the UT level and district level, state level science project competitions. Okay, that is organized by the Department of Science and Technology. I was the assistant senior supervisor of university SPPU theory examinations at the first year level. I was the coordinator of the examination department of the science faculty, the coordinator of the science association of our college. I was the editor of a conference book for the conference which was organized by our institute. I was also invited as a resource person at Homi Bhabha Center for Science Education (TIFR) for summer course in experimental physics that was held in 2016. I have worked as the external examiner for quite a few university final practical examinations which were conducted by the Savitribai Phule Pune University. I am the coordinator of IAPT NGPE examination at our institute and the nearby colleges, that is for the entire district, and I have handled that responsibility for 6 continuous years. I have also served, being a soft skill trainer, I have also served as the coordinator of the soft skill development cell of my institute. I was the assistant director at Central Assessment Program of SPPU examinations. I have also served for a couple of years as the coordinator of the cultural committee, the co-curricular activities, the publicity cell, and the intercollegiate events which were held at our institute. Apart from the responsibilities that I have taken care of at college or university level, I have also been invited as the external examiner for few practical examinations at HSC, that is CBSE 12th level, and that was pre-board examinations. I have also coordinated quite a few institute guest lectures and educational trips for the overall development of our students. Well, 2 achievements that I would like to mention here that I believe are real achievements in all these years of academics that I have served, all these years of service. The first one being one of my papers, along with my PhD supervisor, was accepted and published in the Journal of the Institute of Acoustics US, which is a Scopus Index journal. And not only that my paper was published, but the cover page, I also received the honor that the cover page of the journal for that particular issue was taken from my paper. Okay, the photograph that I had provided, that was made the cover page of that particular journal. Further, in an international conference that was held in Pune, my paper was selected as the best scientific paper, and I received the best scientific paper award for that. conference. So I believe apart from all that that I could do in all these years, these two are an achievement. These two are one of the best, two of the best achievements that I have in these years. Alright, so today we are going to deal with a very important topic in physics, which forms a very important part of the undergraduate physics program in most of the universities in India, and that is oscillations. Right? So, what comes to your mind the first time we'll think of? So today we are going to discuss a very important topic which forms a part of most of the undergraduate studies in many universities in India, and that is oscillations. So what comes to your mind for the first time we hear the word oscillation? Okay, there's something that we have studied all these years, even in schools, in junior colleges and everything. So oscillation, if you have an object, right, which is moving from one point to another point, and it is tracing the same path back, and it is coming to the initial point again. So this to and fro movement of an object, okay, along the same path is known as oscillation. As simple as that, right? So that is what is oscillation. So an object retraces the path back, okay, retraces the path back. It starts from one point, it goes to an extreme, it goes to a final point, and it comes back to the original point, and this continues, this motion continues. So that is what we mean by oscillation. A very simple example of an oscillating body is a pendulum, a simple pendulum. As the name suggests, it's a simple, not so simple, but it is the most, one of the most simple, right? So here is a homemade pendulum. Okay, I don't have access to labs, so that is what I can do. All right, so you have, let us say this is the string, and this is some mass which is attached to the string. So let us say this is the bob. Okay, the bob is generally round, okay, and that we know. So if I just give it a push, so what happens? The bob moves. Okay, so this position of the mass that is attached to the string, this changes with time. So this position is a function of time, and this is what is oscillation. So it is at one point, then it goes to another position, then it goes to another position, then to another position, then to another position, and ultimately it goes to an extreme position, and from that position it again retraces this position, this position, this position back to its original one, initial one. So that is what is oscillation, okay, in case of a simple pendulum. In our life we see many systems which are actually oscillating, many systems which are oscillating. For example, another very simple oscillating system that we know, that we have heard of, is a spring mass system. So if you have a spring, and a mass is attached to it, there is a mass which is attached to it. If I pull this spring downwards, okay, if I pull this, what would happen? This mass would move downwards, and then along with the spring, the mass would go up and down, up and down. So it will follow this path. It will move up, it would come down along the same path, move up, come down. So it moves up and down. So this is oscillation of this mass spring system. Okay, similarly, if I have the spring which is connected to a horizontal surface, suppose this one, okay, there is a spring which is attached to a mass which can be moved along this surface. So if I gently push this mass or slightly pull this mass and release it, what would happen? The mass would also move, okay, along the horizontal. Okay, along the horizontal this would move. So it would, if I release it from here, it would go to this point again till here somewhere, then again to this point again here. So it would retrace this path. So it would move left and right. So that is what is again oscillation of the spring mass system. All right. Now similarly, if I have, suppose I can show you something like this. Now this is also a, okay, suppose I hope that is visible. I have a beaker here, okay, which is filled with water, and I have a small glass bottle. I dip it in the water, this bottle I dip it, and what I see, it's floating, right? It's floating there. I believe that can be seen, okay, it's floating. Now if I slightly push it, gently push it inwards and release, what we see? we see an oscillation. We say this is moving up and down, up and down. Okay, you see this, it has moved to one point position, right? You see this up and down, moving up and down. See, now there are two types of motions that we see here. It is moving this way also, up and down also. At the same time, it is moving this way also, right? It is moving this way. So two types of oscillations it is showing. One is the vertical one, up down, and there is this angular one, right? So two types of oscillations are there. So this is another system, oscillating system that you can find at home. All right, another oscillating system that we can see. Oops, I don't have a, I believe I have a notepad here. All right. So another type of system, if I have, suppose I have this bulb. All right, I gently, is that visible? Yeah. It's quite bright, right? If I gently push it, what do you see? It's moving. See here and there, here and there, right? You don't move the surface, you don't move the surface, you keep the surface stable and you just move it. See, it is showing this way movement. Okay, it is showing this way movement. That is again some type of oscillation. So you can have so many systems. You must have seen the children who are playing with the toys. Their necks are moving, right? Their necks are moving. So if you just push their necks, it would move this way, or it would move this way, right? So these are also oscillations. Okay, so you can have several examples of oscillations that we come across in day-to-day life. Okay, now oscillations is not something which is restricted to only material objects moving. Not true. Okay, so it is not restricted to material objects which are moving. Oscillations can be of any quantities. For example, the electric field, or you say the magnetic field, right? So what is happening? The field is changing with time. The field changing with time. It reaches a maximum, it comes back to some other extreme, and again goes to the other extreme. Okay, the field moves with time. It moves with time. It changes with time, rather. As time passes, the field changes. So field is a function of time in that case. So again, electric or magnetic field, they are also oscillating. Like we have the light, okay, the light that we see, sunlight, let us say, electromagnetic waves. So what happens in that? Both the electric and the magnetic fields, they oscillate, okay, they are functions of time, they oscillate, okay. So all these quantities, they are oscillating, okay, so we come across them. Now, not only these physical quantities like electric magnetic field or material object like a pendulum or spring or mass, but even the most abstract quantities, they oscillate. Okay, the abstract quantities, for example, I take an example of the sine function, the sine wave, let us say sine x. When we write sine x, what happens? As x changes, the value of sine, it goes between two limits. It has an extreme +1 and another one is -1, right? So if I am having a value of x which is changing continuously, okay, changing continuously from 0 to so on, I would have the sine function which is going to a +1, then to a -1, okay, again to a +1, again to a -1. So if x is increasing continuously, then sine would reach +1, then it would go -1, again it would trace the same path, go +1, again it would go -1, and so on. So we say that the sine function, sine is oscillating, okay, the value of sine x is oscillating between +1 and -1 as your x is increasing, as your x is changing. The same happens with cosine, the same happens with tan, all these abstract values, okay, trigonometric functions that we call them. So it happens with all of them, right? So you can have, for example, if you are talking about AC, alternating current, what is oscillating? You have the current value which is oscillating between some maximum value and some minimum. The voltage is oscillating plus V0, minus V0, right? That is what is alternating current we talk about. So all these quantities, they oscillate. So we said that oscillation is not something which is restricted to material objects. moving, okay, oscillating. It can be any quantity which really oscillates. Now, when we know the basics of oscillations, what about the mathematics? How do we write the mathematics of oscillations? So let us see that in brief. We will not go into much details of the mathematics that we do. Okay, we'll just see what are the equations there. Okay, so the basic equation for oscillation is something like this. You have m into a equal to minus kx. So where x is the position of the object which is undergoing oscillation, you have this m is the mass of the oscillator, a is the acceleration, okay, and k is some proportionality constant. We'll deal with that. And why that minus sign? See, m into a, we have from Newton's laws of motion, we know that m into a is basically mathematically given as the force. So kx or minus kx is also the force, okay, kx is the force. So this force is called as the restoring force. It is proportional to the position of the oscillator, the value of x. So f is directly proportional to x. This minus sign tells you that if your oscillator is going in one direction, the force will try to bring it to the other direction, right? So in case of this simple pendulum, for example, if your pendulum, if the mass is moving in one direction, okay, I have the force which is going here. If I release it, what is happening? The displacement is this direction, but the force that is acting on this body, it is trying to bring the object to the point of equilibrium. Similarly, if it is going here, it is trying to bring the object to the point of equilibrium, right? So you have a force which is always opposite to the direction of displacement. So the displacement is here, the force is trying to bring it here. The displacement is going here, the force is trying to. So displacement this way, the force opposite way. Displacement this way, the force opposite way. So this force is trying to restore the equilibrium position of the object. So that is why it is called as the restoring force. Okay, now here I am only referring to those objects or those oscillators for which x is the position and a is the acceleration of those these objects which are undergoing oscillations. Now in such cases what is happening, if you know x as a period, as a function of time, if you know x is changing, okay, with time, then I can write the velocity given as d dt of x, right? I can write velocity to be the time derivative of x. And if I know the value of velocity, then I can write acceleration is further dv by dt. That is, it is the time derivative of velocity. The acceleration is time derivative of velocity. So having known that, I can write from this expressions, I can replace a with dv by dt and further v by dx by dt. So we can write m into d dt of, okay, d dt of a is dv by dt, but what is v? Dx by dt. Dx by dt equal to minus kx. Or I can write m d2x by dt square equal to minus kx, or I can write d2x by dt square equal to minus k upon m into x. So if I say that minus k upon m is again a constant, see, k is a constant of proportionality, m is the mass which is also a constant, so minus k upon m is also a constant, and I write it as minus omega square x, okay, where omega is given by under root of k upon m, and this is known as the frequency of oscillations. Okay, this is known as the frequency of oscillations. Okay, so this is known as the frequency. So this is the equation of oscillations, d2x by dt square equal to minus omega square x. So if there is any system which follows this equation, d2x by dt square equal to minus omega square x, then x in this case will oscillate with time. Okay, the position of the oscillator x will oscillate with time. And how can we write this x? This x can be written as x equal to a cos omega t, or you can also write a sin omega t, a cos omega t plus phi, sin omega t plus phi, and so on. Okay, I'll take the simple one, a cos omega t. So this kind of dependence of x, that is the position on time, this kind of dependence of position on time will result if you have the basic equation of oscillation given by this. Okay, if you have, this is the equation of oscillation. Okay, this is how you give oscillation. This is the dependence of x on t that you would get, and from this what you say is, you say that this is the equation of simple harmonic motion. Okay, so you term this as simple harmonic motion, in this case SHM. You call this as SHM, that is the simple harmonic motion. So in any case of oscillation, if you have a minimum of potential energy for a small oscillation, now this is a term which we will come across quite often, small oscillations. And what do you mean by really small oscillations, right? So the minimum of potential energy for small oscillations if you are having, then this situation will definitely occur. Okay, so for any oscillation you have, if the minimum of potential energy you are having for small oscillations, then you would have these equations, right? Now because why this thing, okay, this equation that we are writing, it also demands that the potential energy, should be of the form V equal to half k x square, or let us write x minus x0 square. Okay, this equation requires that V should be of this form, and this is we know that this is the general expression for a parabola. Now not necessarily every oscillation that you have would give you a V of this nature, right? Would result into a parabolic curve of V against x. For example, I'll just show this. For example, you have a curve of V versus x which looks something like this. Let us say you have a curve of V versus x. Suppose I draw a V with respect to x, and the curve looks something like this. Something random. Okay, definitely this doesn't follow the expression given by this V, alright. But if I consider a small oscillation, okay, and this is your x0, okay, this is the equilibrium point at which your V is minimum, alright. So if I consider a small part, let us say this one, I consider this. So this part definitely can be approximated to follow this expression V equal to half k x minus, that is the parabolic curve. Okay, so this small part, this is that small oscillation we are talking about. So this is the small oscillation that we are talking about. So this part we can approximate it quite easily, that it would be following this expression. Okay, so I can approximate this as a parabolic curve, and therefore for small oscillations, okay, for small amplitudes, that means small oscillations means the small amplitudes, this equation is followed, okay, to a good approximation. And that is why understanding this equation about small oscillations and this minimum V is important, right? Now when we see this expression for x, we will notice one thing for sure. A is constant, that is the amplitude remain constant, it does not change with time. So what happens is, whenever you are writing x equal to a cos omega t, and the limits of cosine function is +1 to -1, right? So if cos omega t is +1, x will be, if cos omega t is +1, x will be given by +a. If cos omega t is -1, x will be given by -a. So in either case you would see that the amplitude of oscillation remains constant. It changes from +a, the maximum value of a, to -a, that is the minimum value of amplitude. Okay, +a to -a. Now in real life systems that is quite not possible. In real life system that doesn't really happen. So what we do to make this equation suitable to real life problems, we actually use another term which refers to the dissipative forces. For example, if this is a pendulum that I see, then what we do, if I simply oscillate it, what happens? You see that with time the amplitude decreases, the amplitude reduces, So the amplitude, so there are many dissipative forces. There is this air drag, there is this friction which is okay, which is there in this system, which is taking part, and we cannot really neglect it in real life situations. It's very difficult to neglect it, and therefore in real life situations we need to have another term which indicate the dissipative forces, and that term is called as the damping force. So you are having damping, the amplitude is reducing. Okay, I'm sorry for that. So you are having damping, that is the amplitude is reducing, and generally the damping force is always proportional to the velocity, like the restoring force is proportional to the position. So you have m d2x by dt square, we write the actual equation, equal to minus kx was your restoring force, and there is this damping force which is given by minus of b into v. So because of this damping force, what happens? X, which was earlier a cos omega t, this has an additional term e raised to minus of beta t. Okay, e raised to minus of beta t. So this term e raised to minus beta t, it decreases exponentially as time increases, and therefore the total amplitude, that is a into e raised to minus beta t, that is the amplitude, okay, that reduces with time. So this is the real life situation that we would have. Now suppose we want to provide an external force to the system, some external force to the system, and that external force itself is periodic. Then what? Then what would we do? So for that purpose, I'll show you another demonstration. Let us consider this system. Okay, and this system, I have used a simple pen stand, and there are grooves on this. I have fitted a broomstick. This is household available, nothing very special. I have just joined it so that it can move, it can oscillate. Okay, so there are some forces which can be applied to this entire system. I'll just show this here. Hope you can see this. Okay, this tip, it moves. Okay, this is the amplitude. So this is oscillating, or this is vibrating, whatever. And there is some frequency that I can give it. I can give it a periodic force, okay, of some frequency I can give. So I will vary this frequency from very low values, okay, very low frequency, to very high frequency, okay, and to intermediate frequencies. And then corresponding, I'll see that what happens to this tip of the the stick. Okay, I'll do it here. I have showed already how this frequency will be. Okay, I hope that would be visible. Okay, limitations on my end. Okay, I just move it very slowly, so a small frequency, and see how much this moves. Okay, I'll keep it at some angle so that against this my blue jacket it will be visible. Okay, how much this moves, just see, just a little bit, right? This is a low frequency. Now I move it very fast. I give this a very, see how much it is moving, very small. Now if I give it an intermediate frequency, okay, this frequency intermediate, just see how much this is moving. Okay, just by a small force that I am applying, the stick is moving so much. Okay, again I reduce, see the frequency, see how the stick is moving. What is the amplitude of this? Amplitude of this motion. If I move it fast, see what is the amplitude. Now if I give it an intermediate frequency, see how much it is moving. Okay, so this tells you that this frequency that I am applying, that is the force that I am applying, what is the frequency, okay, at which I am giving the force, what is the frequency at which my fingers are moving. Okay, of course this is not following that okay, cosine terms or something very precisely, but it would work. So what is the frequency that I am giving, and this has its own natural frequency, and if this frequency that I am providing externally, it matches with this natural frequency, then what happens? This moves with a maximum amplitude, this oscillates with a maximum amplitude, right? And that is known as the resonance. So there is another force that comes into play here, and that force is given by, I'll write it here just to save space and time. That force is given by something like F0 cos omega t. F0 cos. Now this omega is different than, so let me write it as omega dash t. Okay, omega dash t. It is different than this. So whenever we are writing this force, what is happening? What is happening? If this omega, so now we have two terms for x. One, the original one. Let us write that will be b. A cos omega t, and other one will be x equal to a, or let us change the constant, b cos omega dash t. That is this frequency. So in this case, whenever this omega matches with omega dash, omega is known as the natural frequency. Okay, natural frequency. So whenever this omega matches with omega dash, that is the frequency that I am applying, or any applied frequency, then your amplitude will be maximum. Amplitude will be maximum. And that condition is called as resonance. That condition is called as resonance. But whenever they differ, whenever omega and omega dash are not same, then this amplitude will be lower. Okay, it will be lower. So there are three types of forces that we saw. Okay, one is the restoring force in oscillations, one is the damping force, which is the real life situation, and suppose we give some external force so that we have maximum amplitude of oscillations, that is called as the forced oscillation. So in this case, if you are having this force, it is called as force. A very simple example, all of you must have seen your washing machines, right? The spin tub, whenever we spin. At certain frequency, you would see, at certain frequency, whenever we power on or power off the machine, during that time, the drum vibrates very vigorously and we get that sound, dug, 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 dug. So what is happening in that case? The frequency that we are applying through that electrical signals, okay, that is matching with the actual natural frequency of that drum, and that is why it vibrates so much. So that is some practical example. Okay, so thank you so much. I hope you enjoyed the lecture. Thank you.